So welcome everyone to Science Society. Also welcome to listeners later on, and of course a very special welcome to Richard, Joe, and Karen. We really appreciate you coming here. I know it's kind of a little bit annoying to make a Clubhouse account and come here, so we really appreciate it. I prepared a short introduction for Rick, but how about then we do the rest of the intro through an interview format for Joe and Karen, and if that's okay with everyone.
Sure, I think that sounds good.
Perfect. So Dr. Richard Gottscho, he's Executive VP at Lam Research, and if people want to check it out, it's the website is shared in the chat. So yeah, please feel free to click on it and learn more about the company. And he did his education at the Massachusetts Institute of Technology and his PhD in physical chemistry there. And before that, he did his bachelor at the Pennsylvania State University. And he is now at Lam Research for over 27 years, if I'm correct. And it's really a pleasure having you here, sharing this really interesting and I think also really important research you all published. And our question to Joe and Karen, do you want to share like a very brief overview of like your path and where you are right now? And then Victoria usually does a more general interview section after that. Thank you.
This is Karen. So I can give a brief. My background's the same as Rick's in the sense that I have my background's PhD in physical chemistry. Also, I came to Lam about 20 years ago, and I started as a process engineer, which is really relevant to this paper, and that's why we held this competition, because I was a process engineer and wanted to see if the machines could compete with us. So I worked with Rick for many years, for the past 15 years of those 20 years, and have had a lot of fun working with him. And Joe too. Joe I've been working with for the past like 3 or 4 years.
Hi everyone, this is Joe. My background actually is slightly or significantly different from Rick's and Karen's. I had my PhD in astrophysics from University of Massachusetts Amherst, and after that I had additional years as a postdoc researcher also in astrophysics, but later switched my career to semiconductor. Working for them has been more than 5 years. Switching from looking at something very, very big to something very, very small. But surprisingly, the physics is exactly the same, and the methodology I can apply what I have practiced in astrophysical research to semiconductor. It has been very exciting, and it's so much a pleasure to work with Rick and Karen and the rest of the team.
Yeah, thank you so much for sharing that. And Victoria, do you want to go ahead with your questions?
Sure, I'm ready to go. All right, so this question is directed toward Richard and Karen and Joe, and thank you all again for being here. It's wonderful to take the opportunity while you're here to learn a bit of your background, and so to hear maybe how you came to find yourself in the sciences. So my specific question asks you to look back in your life, and this can include in your childhood, and to locate a time or an event or maybe a person through which you noticed a spark that really connected you toward sciences in general.
Yeah, I'll start. It was in grade school for me, I think, and for as long as I can remember, I've always wondered why we're all here and what life is all about and what the universe is all about. Um, and I've been looking for answers to those questions all my life, I suppose. But what really, the seminal moment in my life probably is when I first learned about the Pauli principle and the periodic table, and the rules that govern that periodic table. And I was probably in fourth or fifth grade at the time. So that got me really interested in atomic physics and ultimately quantum mechanics, which is what I did as a graduate student at MIT, doing molecular spectroscopy. I did a slight detour at Penn State. I actually started out in social science, and my first major was sociology because I was actually interested in doing experiments on people. And after taking some classes and reading about studies of such experiments, but when I got into the curriculum, I found it dissatisfying that uh, there wasn't much science in the courses I was taking, and I became frankly bored. So I switched to chemistry, which was almost unheard of at that time, and I've been happily in the physical sciences ever since. Although I have to note that this study we just published kind of brings me back to some of my original interests in doing experiments with people as well.
Yeah, thank you so much. And Karen, it looks like you were about to begin.
Yeah, if you want, I can go next. So funny, nobody's ever really asked me this question, so I need to think really quickly in my head why, how I got here. So I think for me, a lot of it almost was like, why wouldn't I? So my family, there's a lot of scientists in my family. My dad was particle physics, my uncle's physical chemistry, a cousin's physical chemistry. So for me, it was really natural. And also in high school, I took to math and sciences and just didn't do so well in history and English. So for me, it was just what science to do. And I liked math, but I wanted to know how the world worked. So that's when I went into the sciences. But it felt very natural for me in that sense.
Thank you. And Joe, would you care to
Sure.
answer?
Yeah,
Thank you.
I think science came to me also naturally. I remember when I was a little child, I was already very curious about the nature, everything. I was interested in biology, in chemistry, in physics, in math. Um, it pretty much covers all the natural sciences topics, and I think that was when I was still in elementary school. My mom got me a chemistry kit with a lot of chemicals and different instruments I can play around with, and I made a lot of experiments. That was I still remember those moments. And later I was focusing on physics. I so much enjoy physics, and I was so determined to study physics. And I was lucky enough to admitted by arguably the best university in China, Peking University, to study physics. And I just enjoy physical sciences ever since. Later, I started to notice computation created a lot of opportunities for physicists, and I focus my study in computational physics and astrophysics. And in my PhD, I started to develop skills in analyzing data using different type of simulations and machine learning models. I guess that part of the research experience also helped me to have this transition from astrophysics to semiconductor.
Thank you for that journey. It's to all three of you. We appreciate so much this part of the sharing. It's interesting to, you know, we're all here as adults, and then we have this time where we think back to our childhood. And I know that there have been several times when somebody's answer, the answer of a guest, another listener in the audience will share that they had that experience. Somebody was saying they grew up watching, you know, Carl Sagan's Cosmos, and I think it was very popular in China, and we wouldn't have realized certain things, or even hearing Richard when you were mentioning, you know, the periodic table. And I've heard people share that too, even other guests saying, yeah, my father gave me a periodic chart when I was, you know, a toddler, and I've never forgotten it. And your chemistry set, you know, how many of us can think back and remember what great fun that was? So it's a uniting sentiment to hear these your reflections and remember back in our own lives. And it's just also, I like to hear these answers because we're all, you know, we're all here on this earth, and we come in contact with other people and with youth, and we never know when we're going to be responsible for encouraging somebody to follow a path that they really love. And so all of this, all of your answers contribute to just proving how important all of our experiences add up to. So thank you. We really appreciate your answers. And at this point, we turn over the mic to all of you. We're here to field the questions. If we may have a Q&A following your talk, or if you'd like to have it along the way, that's fine. And also, if listeners put questions in the chat, we will share those with you as well. So please feel free to begin, and the mic is yours.
Okay, well, thank you. I'm okay if people want to interrupt me while I'm talking. I think what's important is that we communicate with each other, and the most effective way to do that is to do exactly that. So we don't have to stand on ceremony. I also want to express my personal gratitude, and I think I'm speaking for the whole team, but we're grateful for the opportunity to share our work, which we are, I think it's safe to say, super excited about. It was a lot of fun. It taught us a lot. We think it's quite significant, which is why we went after publication in Nature, and we were tickled pink when the paper got accepted. And the work's continuing. This paper, in my mind, is really the beginning of a journey. It's not the end of the journey. And so having the opportunity to talk about it with people who have expressed interest in it. Many of you I know have read the paper. We got a bunch of really good questions already. Is really valuable to us. To you know, we don't have to rely on a scientific conference or an arranged meeting, a more formal meeting to reach people who are interested. So thanks for that opportunity. So I just titled this talk the same as the paper, Human-Machine Collaboration for Improving Semiconductor Process Development. If you go to slide 2, I'll start off with a little bit of background on Lam Research, because I think the context is very, very important to understand what we were trying to do and why we were trying to do it. And these days, semiconductors are in the news all over the world. Really became obvious during the pandemic when all kinds of shortages occurred, particularly you couldn't get chips to put in automobiles, and the demand for automobiles surged. And yet the automobile manufacturers basically had to shut down their factories because they couldn't get chips. So that kind of brought it to everybody's attention. But I've been in this field since 1980, so more than 40 years, um, and uh, uh, and I've seen, unfortunately, I've seen the rest of the world investing more in workforce development, the education of people, making major investments in factories and R&D centers to bolster their capabilities in semiconductor technology, recognizing that semiconductors are in every electronic device you own. It's at the heart, whether it's smart automobiles or smart washing machines or your favorite smartphone. There are chips in there, semiconductor devices, and it's safe to say that every one of those devices was manufactured by going through one of Lam Research's machines at one point in time. I don't have time to go into how chips are made in detail, but fundamentally, you define a pattern that constitutes a piece of your circuit. You image that pattern photographically or lithographically onto a thin film, and that's where Lam takes over. We will etch those thin films. We'll clean the wafer of the films. That's what I mean by strip. We deposit the films in the first place. And we clean the wafers, and then we follow up those products with service and support. We're a leader in wafer fabrication equipment. We're either number one or number two in virtually every market that we're in. We're in top 5 suppliers worldwide. We're roughly a $18 billion company with more than 18,000 employees. And the company's been in existence since 1980. We have manufacturing, we have research and development, engineering, customer support, and supply chain activity all over the globe. Big presence in wherever our customers are. Most of them, big manufacturers, are in Asia, but also in the United States, Europe, big engineering operation in India as well. If you go to slide 3, this is a more recent addition to the Lam product offering, and we call this computational products. And it was using some of these products in the paper that we published, particularly our ability to do process and integration modeling. And most recently, we had acquired another company, SG Technologies, to allow us to do simulations of the plasma itself. That's at the heart of most of our processes for etching and depositing thin films. So now, if I turn to slide 4, this is the basic problem statement that we're facing. Many of you may be familiar with Moore's law, which isn't a fundamental law of nature. It's an observation that Gordon Moore, who just recently passed away, one of the founders of Intel, that he made, I think back in the 60s. I don't remember whether it was 60s or 70s. And he noted that with the trends of shrinking the dimensions, printing smaller and smaller patterns, that the number of transistors in a chip would double about every 18 months. And that became Moore's law. I've always referred to it as a self-fulfilling prophecy because the industry rallied around these projections and then worked collaboratively and competitively both to make it happen. And that's what you see here in gray. And the scale is on the right. You see it's a logarithmic scale. So orders of magnitude reduction in feature size has led to orders of magnitude increases in transistors per unit area. And with the shrinking feature size, the increasing number of transistors, of course, the cost per transistor has also precipitously declined over those years in an exponential fashion. And that's why all of the technology that is so abundant is enabled. You wouldn't have artificial intelligence playing the role it is today if you didn't have the underlying advances in the semiconductor technology. Now, what's not well understood is during this whole period, the equipment that is used to uh, deposit and etch thin films or do the lithographic patterning has grown increasingly complex in order to maintain the dimensional tolerances that are required in making these smaller and smaller devices. So, to put that in perspective, if you're making a device whose critical dimension might be 20 nanometers or 10 nanometers, the tolerance around that critical dimension might be half a nanometer or even a couple of tenths of a nanometer. Um, Basically, atomic scale precision is required within the chip and for every chip across the wafer so that you have high yield in volume manufacturing, which is essential for low cost. And also, so every wafer has to look within the wafer, all the chips have to look the same. All the chips from every wafer that you process needs to look the same. And every machine in every fab needs to produce a result with a tolerance that's atomic scale. In order to make that happen, we and our peer companies and our competitors have been increasing the knobs, if you will, the control parameters on our machines to enable that to happen. And that produces an enormous complexity, which is what is where we've somewhat tongue-in-cheek dubbed Lamb's law. And the axis on the left illustrates the degree of complexity as measured by the number of recipes we can generate on our tools that makes a measurable difference on the wafer. It may not be a good difference, but it's something that you can detect and measure. And think of a recipe as it's kind of like baking a cake. I mean, if you bake a cake, you know what temperature are you going to run your oven at? How long are you going to bake it? How much flour versus butter versus sugar do you put in there? We're doing something similar, except we're mixing gases like chlorine and argon, boron trichloride, oxygen. We have multiple frequencies of RF power that are used to break down those gases and create reactive plasmas. We have temperature control on the substrate wafer as well as all the walls of the reactor and so forth. And the net result is that today our engineers are looking at a complexity such that, as this plot shows, there's more than 100 trillion different recipes that they could choose from in order to get a desired result. And how on earth do you do that in a cost-effective and timely way? The reality is, if you go to the next slide, it's done using an age-old technique, which we dub Edisonian. It's just like Thomas Edison when he was trying to find the right material to put filaments in an incandescent light bulb, just would kind of go through the periodic table, focusing on the metals, and try one metal after another, and playing around with the dimensions of those filaments until we found something that worked, which was originally a carbon filament and ultimately tungsten. And that's kind of what we do today. We have process engineers who, over many years, develop quite a bit of knowledge and experience. But basically, our customers ask us for a particular set of dimensions on a feature that we're trying to create. You can see that here on the right. This is just a cross section of holes being drilled into a silicon substrate or silicon dioxide, and the dimensions of that hole, the opening at the top, the opening at the bottom, and the profile all the way down are all critical dimensions for making certain devices. So we're given that information from our customers. That's what they tell us they want. And then we have to figure out how to produce that. And we, in this very complicated space of more than 100 trillion different, not solutions, but 100 trillion different possible solutions. And it's a very expensive, time-consuming endeavor. For some of the most critical applications, we might take as long as a year and spend the better part of $1 million and many people working on creating one recipe for a very complicated application. And we would argue that with that approach, we are the whole industry is limited in the rate at which we can progress, because it's very time consuming, it's very expensive. We can't afford to map out that parameter space in gory detail. It just takes too long, too much, and is too expensive. And that's why we refer to this as living in a little data world. I can remember a few years ago, I attended a talk by Jensen Huang, who is the CEO of NVIDIA. And it was just before NVIDIA, well, they were already teamed up with Tesla on self-driving cars. So this was probably around 2014, 2015. And he gave us a talk at Lam. And I got so excited. I said, I've been thinking about this problem all wrong in terms of trying to model everything with physics. All I need is a lot of data. And I was almost euphoric after listening to his talk and seeing how self-driving cars were being trained. Of course, you can equip a Tesla with a bunch of sensors and just drive it around constantly collecting data. The data are actually cheap to collect in that situation. And you can create big data and use big data technology to train algorithms and get those cars to drive by themselves. And we see the results of that. Turns out my euphoria was very short-lived, because I quickly came back to the reality that in our business, we don't know how to make large quantities of data at low cost very quickly. Each one of our experiments costs about $1,000 per recipe, $1,000 for a batch of experiments, and takes about a day to turn it around. And so we just never have the opportunity to generate a lot of data. So I'm kind of getting ahead of myself a little bit. If you go to slide 6, it's basically asking the question, why can't we design a process like we design a chip? If you look at how chips are designed today, the layout of the chip is all done using algorithms, and most recently artificial intelligence algorithms. And for decades now, nobody could make a very advanced microprocessor or memory chip without having a computer algorithm to assist them. And while we've been able to do some modeling in the processing world, in the fabrication world, etching and deposition, it's never been adequately quantitative that allows us to design a reactor, deliver it to a customer, and have it work as advertised. So why not? I've kind of given you the answers to that. If you go to slide 7, basically, ask the question, why not just use physics? We can actually, it wasn't always true. When I first got into the business in 1980, we didn't understand what was going on in these reactors. People had developed techniques to etch and deposit thin films, but we didn't understand the mechanisms. Today, I would argue, because of a lot of really high quality academic research, as well as high quality research in industry and national laboratories all over the world, we understand a lot of the mechanisms. I'd hesitate to say we understand them all, but we can write down equations. The problem is there are way too many equations. There are way too many unknowns in those equations. Too much calibration is required, and the equations are very difficult to solve. Even with today's supercomputers, you have to be smart about how to solve those equations when you're dealing with the fundamental physics. And you'll see that in a couple slides coming up, there are a lot of parameters that, again, you have to run a lot of experiments or a lot of numerical calculations to solve Schrodinger's equation, basically, to come up with those parameters. It's just not practical. Even today, it takes too long, too expensive, too many unknowns. And then I've already, if you go to slide 8, I've already talked about the pure data approach and my false sense of euphoria. And the basic problem here is what I've already said. We live in a little data world. Now, there is an opportunity here, and that is if there were a way to measure, for example, in real time, a high aspect ratio hole that I showed you before, whose dimensions, by the way, for example, in 3D NAND, the top might be 100 nanometers in diameter, and the depth might be 10 micrometers deep. So you've got aspect ratios, the better part of 100 to 1, and you need to control that profile to maybe a few nanometers. That's actually a pretty big device, but it's a very challenging application. If you could measure that profile in real time with atomic scale precision, it would break this little data problem. But nobody's been able to figure out how to build a piece of metrology that does that. And instead, what's done is you do partial etches. You put a piece of a wafer in there, you dial in a process, very Edisonian. You take the piece out, then you have to destroy it in order to get a cross-sectional image using transmission electron microscopy typically. And that's where the cost and the slow turnaround comes from. It's a destructive metrology, and it has to be done over and over and over again. So for now, that's the reality, and it forces us into this little data world. So the question is, pure physics doesn't work, pure data doesn't work, but a hybrid approach of data and physics is actually much more powerful. And if you go even further, which is the subject of this paper, if you combine human ingenuity, human experience with data, with physics, then you can really change the paradigm. So if you look at slide 9, let's go into a little bit more detail. This is what we want to do. We want to consider how to create this memory hole. So this is actually looking at a so-called 3D NAND device, which is at the heart of all your USB cards, flash cards that go into cameras. They're all today NAND flash memory, and they're all 3D NAND flash memory. And that's only been true in the last about 5 years, I would say. And you can see here outlined in cyan, gives you some idea of the dimensions of that structure and how it has to, how difficult it is to do something with that kind of aspect ratio. You can see the blow up on the right, which illustrates how precisely you need to control the sidewall characteristics as you're etching that structure. And then, by the way, you have to fill it up again. You're filling it up with metal liners and dielectric materials. So the filling processes are also equally complex. So the way we decided to approach this, and this was really Karen's thinking that instigated this, was it was she was motivated by having read about how computers were designed to beat the grandmasters in chess, and could we turn this problem into a game? And the idea was, if we could turn it into a game, then we can test how good one player is at winning that game versus another. But more importantly, what we were really looking to do was, how can we test one algorithm, some hybrid algorithm between physics and data, as I alluded to before, how well does it perform relative to the human and relative to another algorithm? And then, so that's what slide 10 is showing. The other point of doing this, making a game out of this, is the game is done in a virtual environment, and the reason it's done in a virtual environment, again, is because of the cost and the cycle time of generating data. If you wanted to compare one algorithm to another, it's prohibitively time-consuming and expensive to generate the data for each algorithm or for each person. So if I want to compare one person to another, I give them the same problem. I have to give them all the same materials. I have to give them time on the machines. I have to give them time on the metrology. And I have to spend a lot of money and a lot of time to get a data set. And then it's going to be confounded further because there are sources of variability that we can't always control. The reactors, the states of the reactors drift in time. The incoming material has some degree of variability. No two wafers on which the chips are made are exactly the same. No two chips are exactly the same. So the data would be confounded by all those sources of noise. And I'll come back to the noise challenge a little bit later. So we decided to build a virtual environment. That's slide 11. And let me just pause here in a second, make sure everybody's still with me and you're able to follow along. And slide 11 is showing virtual environment for high aspect ratio etch. Yes?
Yeah,
Okay.
I'm still here. But if anyone has questions, please, please
Okay.
share in the chat. Thank you.
So we built a simulator. Actually, we had pieces of this simulator from our computational products group, a product called Coventor, and we sell that externally. We have a version of it that we've created that's only available inside Lam at the moment, which was the version that was used in this study because it's based more on fundamental physical mechanisms. So we start with an incoming profile on the left here, akin to what our customers would give us. They give us a patterned film and ask us to transfer it into an underlying material. We chose, this is a very simple example with a photoresist mask. That's what's patterned photographically. And then we're trying to transfer that pattern into an underlying film of silicon dioxide. We have 11 parameters that we can tune in our reactor, and you can see those on the pressure, plasma power one. So there are two different sources of plasma power, two different frequencies, a bunch of different gases, and you can time modulate the application of the power. It turns out there are good reasons for doing that. So there's a pulse duty cycle, there's a pulse frequency, there's a wafer temperature. The output parameters that are comparable to what our customers will demand is how deeply did you etch, how fast did you etch, that's the etch rate, how much mask do you have remaining. The customers never want to see the mask disappear because then you lose dimensional fidelity in the pattern you're trying to create. And then as I mentioned before, you have a top critical dimension, a delta critical dimension, which would be the difference between the top and the bottom of the feature, and then the bow critical dimension, which corresponds to the maximum opening of the hole as you go down this high aspect ratio hole. Those are typical requirements that we have to meet with very strict tolerances and very small numbers. And then we have a simulation engine that takes those input parameters, the recipe parameters, and then simulates the profiles that you can see on the right. We have our targeted profile. That's what our virtual customer is asking for. And then, but along the way, you might find a wide variety of different profiles, none of which meet the requirement. And then, as I said before, we assign costs which are roughly equivalent to what we see in the real world of $1,000 per recipe, $1,000 for a batch of recipes. In these experiments, there was no source of variability, so it's really best case. And the goal of the game is develop a recipe that meets the target spec with the lowest cost to target, which will also almost surely correspond to the fewest number of experiments and therefore the least amount of time. And of course, the old adage of time is money absolutely is applicable here. So if you go to slide 12, it's just a little bit more detail on how we created that virtual environment. As I said before, Simulator 3D in the middle basically takes these kinds of parameters, ion energy, etch and flux, depositor flux, and so forth, and we run a mechanistic simulation that is physics-based in order to generate the profiles. And from those profiles, we do virtual metrology to extract out these 6 output objective metrics, etch depth through bow CD. One of the innovations that the team came up with was how do you map the recipe parameters to the fluxes that are used by Simulator 3D? That's an active area of research. There are a variety of ways to do that. The approach we took was largely combing the literature both inside Lam Research as well as outside, and coming up with 48 analytical equations that connect those two with 74 constants. And those constants have to be assigned based on physics, ultimately, to make it realistic. And there's an important point here. This simulator and this virtual environment, we say, is sufficiently realistic such that we can get valuable learning out of it, but it is not precisely predictive in that you can't take the results of these simulations and this modeling and go into the laboratory and dial in that recipe and get that result. It's not accurate to that degree. And one of the learnings for me in this study was it's okay as long as it is sufficiently realistic. You can get valuable learning that is transferable to the real world. And I'll come back to that at the end of the talk. I think sufficiently realistic is what is meant by that is perhaps an interesting philosophical question. I don't know if it can be answered mathematically. The way we answered it was we just asked the process engineers, beginning with Karen, as to whether or not this felt like they were developing a recipe on a real tool. And the answer that came back was, yeah, it's just as frustrating as doing it in the real world. And that's even with simplification, because 11 parameters is actually less than typically what we're dealing with. And we might be dealing with 16 or more parameters that we have to choose from, and over a wide range of settings. So now if we, so that's what we set up to do in the virtual world. And there's a lot of engineering that goes into the simulations in order to make them run sufficiently fast that we can get results in a reasonable period of time. Slide 13, we start to take a look at what we learned and what the results look like. So, and the basic conclusion you can see at the top of this slide is that newborn machines are no match for expert engineers. There's a lot of comforting data in here if you just start on the left. So you can see there are 6 plots here of slightly different colors of blue and green. Senior engineer, 3 different senior engineers and 3 different junior engineers. Senior engineers had a minimum of 7 years of experience developing recipes for customers on real tools like we were trying to do in the virtual environment. The junior engineers were people who had technical degrees, technical background, but no significant experience in doing high aspect ratio dielectric etching. And it was quite comforting to see that the senior engineers consistently outperformed the junior engineers. So you could see quantitatively the value of experience and domain knowledge. And on average, it was roughly a factor of 2 better. So the best senior engineer played the game and won, spending only $105,000 virtual dollars. The junior engineers were typically over $200,000. We gave the same problem to some volunteers from our human resources department. You see that in the middle. And you can see they got stuck. The best person got stuck at around 20% off of the target. And but none of them converged to hitting the target before they'd spent $500,000 virtual dollars. And so we just cut off that experiment at that point. Similarly, and somewhat surprising initially, we gave the same problem to data scientists who had access to a variety of algorithms, and every data scientist, I think, has their own favorite approach. And they actually didn't fare any significantly better than our colleagues in human resources. They couldn't compete with the process engineers. Now they were starting with no prior knowledge, no way to filter the parameter space to get started. So that was the initial result, and as I said, it was confirming our biases with respect to the value of experience in a technical education. And it wasn't too surprising to me that the data scientists couldn't do much better, because the, the the machines were like I said, they were newborn machines. They had no prior knowledge. If you go to slide 14, what we did is we then went in and looked at the expert engineering learning trajectories, which is measured by the distance to target as a function of the cost. And there are two distinct regions in this learning trajectory. And it was very intuitive to us because we see it all the time. There's an initial phase, which we call rough tuning, where experienced engineers have a pretty good idea of which knobs to turn and in which direction and by how much, such that they progress very rapidly towards the target. So within a few experiments or a few batches of experiments, they get down to within 20% or less of the target. But that's when the trouble begins. And that's, if you're a process engineer, that's actually quite rewarding. I think it's always fun when you're trying to solve a problem and you initially make very rapid progress. But then the problem sets in is they got stuck and they bounce around such that about 80% of the cost is spent trying to close the last 15 to 20% of the distance from target. And that's what you see plotted here on the left. And our explanation for that is that at this point, you've got to tune a number of parameters simultaneously in non-intuitive ways, where even experienced engineers really don't have a good feeling for what to do. And so they try things. Sometimes it gets a little better, sometimes it gets a little worse, and it takes them a long time. So 80% of the cost is in that fine-tuning phase. And that actually began to get us thinking about, well, how do we solve that problem using machine learning technology? So if you go to slide 15, what we said was, okay, let's share some of that learning from the expert with the data scientists. So we'll transfer the results of the human designed experiments at various points along the learning trajectory. So the first point you see here, we refer to that as transfer point A. We transferred that knowledge by way of, okay, we ran these experiments. These are the results we got. We give that to the data scientists. Now they have some prior knowledge, and they go off and run their algorithms. And what you see is that, and we have to do this over and over again, because there's some stochasticity in terms of the design of experiments. So we run many experiments. I think Joe or Karen, you correct me. I think each one was run about 100 times, right?
Yes, 100.
Yeah. And so we just measure the success rate in terms of how many times out of those 100 different experimental designs does the machine learning algorithm beat the best human. And you can see here that on average, we're about 42% success rate, which isn't very good. And you can see the learning trajectories, attempt 1 through 6 out of 100. So it just isn't, they're just not getting enough information at transfer point A. So then we go, we went to transfer point B, C, D, E. That's what those black dots represent. And you can see transfer point B, the next one, is close to the knee in the learning curve. So if you go to slide 16, we actually jump to point C, which is the third point. And now we're starting to see greater than 90%, much greater, 99% success rate. And you can look at the learning trajectories, and it's quite informative. So in this case, the 6 out of the 100, every one of them was significantly beating the best human engineer with the most experience by about a factor of 2 in almost every instance. The other thing that I find really interesting here, and it's really built into the design of the algorithms, but the first thing that the machines do when they're given this prior knowledge at point C is they they start exploring the parameter space to understand what is going to be most productive in terms of getting to target faster and cheaper. So the first thing that you see here on these learning curves is the first experiments all go away from target, and that's indicative of the machines prioritizing exploration over exploitation initially. And with that added information added to the expert process engineers' design of experiments and the results of those experiments, they're able to subsequently converge quite quickly. If you put all those data together in slide 17, and you see the sweet spot point C, where there's a V-shaped curve. So as I talked about earlier, if you transfer too early, basically we haven't generated enough learning for the machines to converge faster than the expert human. If you transfer the information too late, then you've basically wasted time and money with the expert process engineer wandering around in this fine-tuning space in a very non-productive way. So the conclusion is there is an optimal transfer point. The obvious question is, how do I know where that point is? And I think that's still an open question, but our bias would be as you enter this fine-tuning phase, that's when you should start thinking about transferring knowledge to a data scientist and a machine learning algorithm, and the probability is that you'll beat the best human engineer. If you transfer a little late, you're not going to necessarily save a factor of 2, but there are substantial savings. You can see that in the plot here. Even at point E, you're saving about 30%, as opposed to point C, where it's closer to 50%. And there's a distribution, of course. So when I quote those numbers, I'm quoting a mean or a median, I guess. So then I'll just wrap up with the last slide here, conclusions. That the R&D, I think the little data problem is generic to R&D in general. I'm sure there's some exceptions to that. And the reason I say that is the very nature of research, particularly research, a little less so in development, is you typically don't generate lots of data, because even if you get a promising result in research, you typically want to go in and change something and try and understand what the trends are, what the opportunities are. And so you don't build up large databases that are consistent. And the cost of doing those experiments is usually prohibitively expensive. The time is extensive. So what we conclude is that to deal with that problem, you really have to think about strategies that take each datum generated in the R&D world and treating it as a precious commodity and leveraging that learning to the maximum extent. The second piece of learning here is that, as I said earlier, models don't have to be accurate to be useful. They have to be realistic. How you define realistic is an open question. But and to drive that point home, as I said before, we couldn't take the results of this simulation and go in the laboratory, dial in the recipe, and get a quantitative result that matched the theoretical prediction. But what we could do is take the methodology, that is the algorithms that were deployed to have the cost and the time to get to the targeted result from our learning in the virtual world, apply those algorithms in the real world. We have done that, and they do work. There are some challenges, again, with respect to noise, and that's an active area that we're still researching. As you might imagine, as you introduce noise and variability, the efficiency or the effectiveness of the algorithms is compromised to some extent. But the basic approach does work and has value in the real world, even though the models are not precisely predictive. Of course, as they get more and more data and get more and more quantitatively accurate, they will become even more useful, but they don't have to start out that way to be useful. The virtual environment, we believe, is a very rich environment for workforce development, for training people how to be process engineers. You can give them challenge problems. Today, that's done by throwing people in the laboratory and typically teaming them up with an experienced engineer. But it takes them quite often years to build that expertise and capability, and there's a lot of time and money spent getting them there, and they're using assets. These machines cost millions of dollars, and if they're being used to train people, they're not being used to solve customer problems. So there's an enormous value proposition here in the virtual environment. Again, even without its being quantitatively precise or accurate. Give everybody the same challenge problem, and you have built-in analytics. You can clearly see if somebody is better at developing these recipes than somebody else, and it gives you the opportunity to team people up, that somebody who's struggling can be teamed up with somebody who has more experience, better intuition, and accelerate the learning for the person who is struggling. So I think we clearly showed the virtual environment enables us to speed up the time to solution, and time is money. It also cuts costs. So last slide, Joe is online and Karen's online, but this is the total group. Everyone had a different contribution, which I think is outlined in the paper, what everybody's contribution was. But it really was a team effort. And the diverse backgrounds and experience of this team was absolutely essential for our generating this learning, generating these results, and successfully getting them published in Nature, and allowing me to present this work to all of you. Thank you.
Yeah, thank you so much for this really wonderful presentation and explaining really well the context, and yeah, it's so different, to read a paper or to have you and your team presenting it here and explaining it. And I don't know if Joe and Karen wanted to add something before we go into questions.
Yeah, I didn't have anything to add. I think Rick did a great job covering it, but happy to help answer questions if any.
It's an enjoyable talk. Thank you, Rick.
Okay, perfect. So please either share in the chat or unmute if you want to ask a question. I know, VTR, you've been here for a while. Did you want to ask a question, add a comment right away?
Hi, Katrina. Yeah, I've been here present, and I had something come up, but I'll wait, and I'll definitely have some questions that I want to ask. I'll have other folks go first.
Okay, sure. Dr. Shah, did you want to ask a question, say something?
Yeah, thank you so much, Richard, for your wonderful presentation. Hopefully you can hear me because I'm driving. So I remember I was not able to, concentrate, but I remember in one of the slides, if I remember it correct, number 17, you mentioned about the Z curve and there was an invert region, if I am right. So based upon this information that you got, you mean that the AI was not some sort of, we are talking about alignment and not alignment, so it didn't align, right, based upon whatever we have in slide 17.
I'm not sure I understand the question. When you say the AI is not aligned,
You mentioned that about the learning curve, and I was just
yes.
wondering, based upon this graph that you just provided in slide 17, and specifically statically inverted region. What other information you can share with us? For example, when we are talking about the AI, some sort of, um, for example, we can use the backward state space search. So did they try those kind of things? Because aesthetically, it has a different meaning than the AI learning, and I was wondering maybe you have further information that you can share with us.
I think I'll defer to Joe to try and answer that question.
We actually tried a bunch of different algorithm on this virtual game, and this is specific plot seen in page 17 is a specific algorithm as a representation of a class of optimizing algorithm. We are still researching other possible algorithms. And I agree with you, there are other possible candidate algorithm can attempt this game problem. And actually, this is exactly the value of this game. It allows us to test the different algorithmic ideas with nearly no cost.
I see. That was my question because aesthetically it has a different meaning than AI. So thank you so much.
But I think also that that inverted region, the reason the cost is increasing and why there appears to be a minimum. And so I think if you look in the paper, you'll see some of the minima are more pronounced than others. That's a function of the algorithms being used. But I think the overarching reason why that cost increases is just because you're wasting time and money with the expert process engineers' design of experiments in a regime where their experience doesn't add much value.
Exactly. Maybe that's why that there's a topic such as, for example, diverse application that they are using. Some of the companies using AI for the diverse applications, and it helps sometimes through the AI learning. Thank you so much for your answer.
Yep.
Yeah, thank you for that question. Maybe in the meantime, I'll ask a few that I wrote down and shared earlier, because some of them were a little bit related to this. So maybe we can go into some of them. So one question was, how might domain knowledge be encoded into these computer algorithms to enhance the capability in process engineering the semiconductor chips?
Yeah, so that's a good question. And effectively, what we're showing here is one way in which that domain knowledge is encoded is this hybrid human first, computer last approach, where the human domain, the domain knowledge that resides in the human is transferred to the machine learning algorithms in the way that I described. So you pick a transfer point and share all of the results of those design of experiments, which then enables the algorithm to start with some knowledge. But there are a variety of ways in which you can do that. An obvious question is, how do we impart that domain knowledge into the machine learning algorithms without the humans running any experiments on a new problem? So transfer it. If you go back to slide 17, for example, where it says no human and the results are terrible with our current approach, the challenge is, how can you get the machines to, how can you impart domain knowledge? How can you teach them physics, if you will, such that you don't need the human design of experiments initially? That's an active area of research.
Yeah, I think that's really interesting for various reasons. Also, do you think that this might be applicable then in the future for other solutions? Let's say to figure out in huge data sets, let's say from hospitals, why people die under special conditions, what are the factors? Because does it kind of address a little bit this black box problem that we don't know necessarily how these AIs come to the results, since we initially encoded this domain knowledge and kind of is that kind of translated into a little bit of a common sense, human common sense encoding?
Yeah, I don't know. I'd really hesitate to generalizing it to something like medical care. Um, I think the opportunity here is, can we figure out a way to encode the physics as priors, if you will, into the machine learning algorithms, such that we don't have to spend any time or money designing experiments with an expert process engineer, and yet we can still get there as quickly. So that I don't know, Joe, do you want to add anything, or Karen?
Yeah, I can add just a couple of those sentences here. When you really deal with a very complex system and you want to optimize it, you can, one way you tackle the problem is you consider your complex system as a black box. So then you fully rely on the feedback from the black box to make a decision for your next experiment to achieve your desire. But as we discuss here, yes, there are a lot of other applications where we already accumulate quite a bit of knowledge. So in that sense, if you can turn that black box into a gray box, so then maybe solving the problem can be a lot easier. But I guess we are touching the critical question: how to turn a black box into a gray box.
I have another comment. You mentioned intuition, so I thought it was kind of interesting. It almost seems intuitive or obvious in retrospect that you might have the human go first and then the computer go last. It's almost like, well, that makes sense. But it was actually kind of surprising, and you might even consider it counterintuitive, because at the beginning of the game, there's the most number of possible combinations. And so you might think that with the most number of options and combinations, that maybe the computer would be able to tackle that better. Humans can't fathom so many combinations. But if you look at a chess match, the first computer chess game also focused on the last two moves. And even today, it relies on kind of human guiding the first moves, the opening moves of the chess game.
Yeah, that's really interesting. And I had for that kind of a follow-up question noted, if it still makes sense to answer it. It was how might prior beliefs be used to incorporate this domain knowledge into the computer algorithms?
Yeah, I think it's essentially the same question.
Yeah, yeah, I don't know.
We go
Okay,
ahead.
yeah, okay, yeah. I mean, from the physics side, maybe yes. From maybe like medical knowledge or other like less engineering problems, maybe it's a little bit different. Because we have kind of, human collected kind of knowledge that we don't 100% researched, like that is like a fact, real fact, but we kind of do it anyways, most of us. And it would be interesting to add that and see if you can confirm or basically or kind of disregard those beliefs we have, why we do certain things, if those are really better, or I don't know if you know that, but let's say in a lab, I used to do a lot of electrophysiology. We do a lot of steps. It's kind of almost superstition that we do all these steps, and everyone has their own kind of different recipe and strongly believes that this is the most important part for it to be successful. But it's not real, nobody really analyzed it and proved that this was the most necessary step. I don't know if in engineering steps for semiconductors there are similar things like this.
I think there are a lot of things in the process flow in making a chip that get locked in because of some experiment many years before that led people to certain conclusions that may no longer be valid, but no, everybody's afraid to change the procedure because of the unknown.
Yeah, exactly.
So
And
I think
that's
the
not
analogy is there.
yeah.
Yeah.
Yeah, so that's not really knowledge, domain knowledge. It's kind of more of a belief.
Right.
I think it would be interesting to skip a lot of those probably useless steps that are more superstitious than anything else.
Yeah, and I would argue again, testing some of those hypotheses in a virtual environment is probably likely to be much more fruitful than trying to do it in the laboratory, in the real laboratory.
I had a question, guys, if I may, and I hope I'm not interrupting anyone. So the whole process that you're using statistical learning and pattern recognition to make the etching process better or find new discoveries, because there is an inherent you mentioned Moore's law, right? And we are coming almost towards the end of Moore's law with the amount of transistors we can pack in a space. It comes into heat effects, quantum effects, and even 3D stacking causes more heat effects. Like, is that the goal here to optimize what we have, or to push the the I think we are at 3 nanometer, what we are at 5 nanometers right now, not sure, to push that uh, number of transistors that we can pack in a space.
Well, there are a lot of efforts to continue that on Moore's law curve. As I said, I've always viewed it as a self-fulfilling prophecy. The manner in which it's being done today is very different from what was being done even 10 years ago, let alone 20 or 30. It's not all being done by making things smaller. The 3D NAND is about, actually the devices are bigger, but now they go in the third dimension, which gives you an enormous boost in density. So there are a lot of different strategies, but the trends are all there to pack more and more devices and functionality in a smaller volume at lower cost.
Did you have a follow-up question, Vitya?
Yeah, so maybe I was trying to get at again to the larger goal of this is for optimization of the workflows, or I'm trying to get a basic understanding of whether
Yeah,
this is
this work was primarily motivated by trying to deal with the ever increasing complexity of our solution space, which drives cost up in R&D and delays solutions getting to market. So if you think about the competitive dynamic for Lam Research and the people we compete against, we typically win by being there first. And by being there, I mean with solutions that meet both the technical and economic needs of our customers. So one of our major motivations here is to speed up the rate at which we can figure out how to meet our customers' requirements for a given technology node, for a given application. Uh, by application, I mean etching a high aspect ratio hole or forming a nano sheet in a logic device. It's kind of a floating cantilever that becomes the channel for the transistor. There are many, many different applications, many different requirements. They all have to come together in a given technology node. And so getting there faster, cheaper is a source of competitive advantage.
Got it. So I think from my understanding, so this is like custom chip design too, right? This is
No,
something.
there is a lot of logic chips today are highly customized and tailored to the application, particularly for AI
Right.
applications. But memory chips are not. So it really depends on the device. There's a high degree of, there's a whole variety of memory chips too. There is some specialization, some sub-markets, but most memory devices are the same, fundamentally the same.
And with the von Neumann architecture, we run into the same memory bottlenecks, right? For processing and fetch decode cycle, like the clock cycle, there is a fundamental limitations there to how the instruction sets gets loaded. How are you guys trying to explore that space with this, or is it maybe I'm
Not per
off?
se. That's really the domain of our customers' customers. So that's the domain of the Googles and the Amazons and the Nvidias of the world, perhaps. I'm certainly no expert in that space, but my understanding, none of this per se relieves the problems associated with von Neumann architectures. There's a lot of work being done on different architectures that are not von Neumann, in particular neural nets. And how can you do in-memory computing? So you don't have to transfer data across a bus. Those are active areas of research. Lam Research supports that activity because we, again, provide process solutions that enable those structures to be built.
Right. Got it. Thanks.
Yeah. I just want to respond to a good comment. Mustafa in the chat room, is human superiority over AI and rough tuning structurally permanent or only in the current state of AI? In other words, with the dizzying development of AI, should we expect AI superiority and rough tuning as well? That's an excellent question. I don't think we have an answer to that. My gut tells me is no, we're not done. As actually I said at the beginning, this work is the beginning of a lot more research that can be done to answer a lot of questions like this one. My personal belief is while it will happen someday, I don't think it's near term because there's still a data size problem. And if you look at the rough tuning phase, the space is so vast. How to teach a machine where to go at the beginning without a lot of data is where the challenge is. And there needs to be a breakthrough there.
Yeah, thank you for noticing. I was about to read those out, and thank you, Mustafa, for sharing them. And I think it's Joyce, please go ahead if you have a question.
Yeah, from a non-expert point of view, I just thought I would throw out a couple questions. One is, are there any stories about how you arrived at the idea of doing it as a game? And then the other question to put out there is there any particular favorite application that you're looking forward to the advances in the semiconductors being able to enable? Thank you.
So I'll let Karen answer the first one. I got to think more about the second one.
All right, so how we thought about turning this into a game, or how this kind of initiated. So I mentioned at the beginning that I was a process engineer at Lam when I came 20 years ago. I was a process engineer for about 7 years. And about 5 years ago, by the way, I hear an echo. I don't know how to get rid of that. About 5 years ago, I noticed
Somebody
that.
needs to mute.
Yep, there you go.
Okay, that's better. Thanks. I noticed that either at conferences or in the hall or even at a work party, data scientists were coming up to me and claiming that they could optimize a process. If we only gave them the data, they could plug it into a machine, a computer, and out would come the process recipe. Why are we complaining about how hard it is to be a process engineer? And I had no way to know whether I should believe them or not. I had no benchmark, no comparison. I didn't know if they understood how hard it was to be a process engineer. And I wanted them to understand that it wasn't just they needed to find a recipe, they needed to find it faster and cheaper than we already could with a human. And so originally I thought about doing a real experiment in the lab with real wafers, with real test wafers. And I went to Rick with that idea, and he said, that's going to be way too expensive. Way too much variability. How about we do it virtually? So that's where that idea came up. Once we thought of doing it virtually, the rest was smooth.
Yeah, and I would say,
Yeah, thanks.
we were inspired by. I mean, I was inspired by AlphaGo beating the best human in Go, and the way in which AlphaGo learned, as best I understood it, where algorithms were pitted against each other. So that got us thinking about gamifying it as
Right.
well.
I didn't mention that part of the game is it was inspired by the chess and Go games, specifically by Gary Kasparov and Deep Blue and those games that I'd read books on and we've all heard about.
Yeah.
So
And then
I had a quick
second
question. I just saw the slide where it talks about the physics. Which slide number is it? Let me just pull it up again. So it talks about the physics-based mapping. Could you explain a little bit more what that means?
Karen?
So I don't have this slide right in front of me, but could it be that we're describing how we made the virtual game?
It's basically connecting the recipe parameters or knobs on the reactor to the fluxes and energy sticking coefficients and etch yields that are inputs into Simulator 3D. So what I'd said earlier was there's a lot of data in the literature where people have studied the properties of these plasmas and measured ion densities, electron densities, and even their velocity distributions. I did a lot of that in my early career at Bell Laboratories. I measured electric fields, measured densities, so forth. And there's been a lot of simulations based on physics, using a lot of data that's generated. For example, to model these things, you need to know the probability that when an electron at a certain energy impacts a molecule, that molecule will break apart into various constituents. What's the probability it's this constituent, that constituent? In what energy states are those are they excited electronically, vibrationally, even rotationally? All those have different probabilities. People measure them, people calculate those things. That's what I was saying earlier. There are too many parameters, too many equations to do it without being smart about it. So this physics-based mapping is smart about it. Despite all that complexity, a lot of the behavioral patterns that connect, okay, if I increase my pressure, what happens to my ion energy at the wafer? Or what happens to the flux of chlorine atoms and so forth, reduced to fairly simple functional forms. So we took those published functional forms either through Lamb internal work or what was in the literature, and created a mapping over a, a parameter, a fairly wide range of parameters. So pressures go from 5 millitorr, for example, to 1 torr. I mean, I don't think we did that range, but it's in the paper. We published the ranges in the paper. So that's what that physics-based mapping is about. So it gives us a set of analytical transform functions, if you will.
Got it. So like a observation mapped with the reasoning behind the possible, like the probability of uh, uh, some kind of event happening based on the observation, right?
Right.
Or
So, yeah, I kind of went down a tangent with the complexity of the reactions. The reason that the reactions reduced to fairly simple, the equations reduced to fairly simple forms. I have a very simple-minded way of explaining that. If you're an electrical engineer, and you have a complicated circuit of resistors, for example, or you could do it with capacitors, and you know that two resistors in series, the resistor that's most important is the big one because the current has to go through both of them, and the current limitation is dictated by the large resistance. If the resistors are wired in parallel, it's actually the small resistor that is most important to think about. You can almost neglect the big resistor because all the current will go through the path of least resistance.
Kirchhoff's law.
So
Yeah.
yeah, right. So there's an analogy in chemistry. So you either have slow reactions or fast reactions, and reactions sometimes go in parallel and sometimes they go in series. So you have this enormous complexity in chemical reactions going on in a plasma, reactive plasma, because every energy state of every molecule has a different reaction probability. But it all condenses down into very simple forms, I think, because again, the only reactions that really matter are the rate limiting ones. Or if you got something going on in parallel, it's the one that goes fastest.
You have encoded these sort of, like, I would say, an ontology or like sort of rules about these mechanisms in the system, or it's just statistically pattern matching everything? Is it?
We encoded to make the virtual demo, the virtual process on which we tested. We did encode specific equations. It wasn't a probability. It was we did use data that I collected as a process engineer, and diagnostic data, but it was encoded in equations and in the simulator.
Yeah, there's semi-empirical equations. And that's why, again, this virtual environment is not precisely predictive. It's not quantitatively accurate. But it's also why it's realistic, because we're using behavioral patterns that have been observed and modeled and modeled as well from physics.
Got it. Cool.
Okay. So there was a previous two-part question. I think the second one, if I recall correctly, was are there any particular applications which we're particularly interested in or excited about? Was that the question? I don't know if she's still on.
Yeah.
Okay. I think everybody probably has a different answer to that question. Mine is not really. The space is so rich, and I've been struggling with it for decades that to me it's just super exciting to have this kind of capability. When I started my career, I was asking that question: why can't we design a process to make a chip like we design a chip? And I thought it would not be so hard. So you know, there's a tremendous number of problems. This particular example we're talking about here is not a realistic pattern that would be fabricated, because the mask is too simple. The film being etched is too simple. Usually, these are layers of different films that you have to go through all in one process. And the process recipes are not a single recipe; they're multiple recipes that are ganged together. So the complexity gets even greater. So just dealing with that problem, and that's obviously something we're working on, is a very rich space to learn. I don't know if that answered the question, but that's...
Yeah, thank you. How about Joe or Karen, if they have any that they're excited about?
The part I am very excited about is we were able to build a machine that can collaborate and compete with human, and in certain circumstances, the specifically this human first, machine last scenario can actually substantially reduce the cost. There is a part of the story we didn't talk about. Actually, before we work on the game published in this paper, Karen actually had a earlier version of the game. Rick was able to solve that problem with very small number of moves. But the machine learning capability we had at that point had a lot of steps. However, we were still inspired and encouraged to improve the algo. And then we ended up with this piece of work that is published. So I think this this whole learning process is very, very exciting.
Yes, thanks.
Thank you.
So people want to continue to talk. Mustafa's got more questions, and Eric has some questions. I could try and deal with some of them. The
I have a couple
virtual...
questions first, if that's okay.
Oh, go ahead.
Hi, Rick. Thanks for this talk. Thank you, Katerina. It was really interesting hearing the layout of the entire process and understanding the history a bit. I was curious about probably something that's more fundamental, but you had mentioned earlier in the manufacturing part of the talk about how there are two different types of plasma that are being used in this process. I was curious why that is.
Why there are two different manufacturing processes, did you say?
Two different types of plasma that was used in the manufacturing process.
Well, there are actually many different kinds of... There are many different ways of generating the plasma, not just two. And there are deposition processes and etching processes that use plasma. There are deposition etching processes that do not use plasma, but use just reactive gases. And I have to apologize. I just realized I have another meeting that's beginning right now that I'm actually late for. So I will have to sign off. But I want to thank everybody again for your time and for the invitation to allow Lam to share their work with you and to answer your question, get your feedback. So it's much appreciated. Thank you.
Yeah, thank you so much for giving us the time and sharing the knowledge and this wonderful work that is kind of, pointing towards the future, what we can do as humans with AIs. And I will look forward to learning more. And it's really interesting pioneering work that hopefully will get adapted in more fields. So thank you so much for doing the work and for sharing it with us and answering so many questions. We appreciate it.
Thank you. Bye-bye.
Thank you. Thank you.
Yeah, Karen, do you wanna still? Oh, she left. So I'm sorry that we didn't get to all the questions. Maybe if you want to share some with me, I can try to forward them to Rick and then address them later on. We are actually switching to our next room. We had the science. Oh, Karen, you're back. Did you want to hang out a little bit longer?
I'm
And
back. I saw everyone was leaving, so I hung up, and then I heard the last session when it was already hanging out.
no, it's fine.
I just
If you have a couple minutes and if you want to answer the couple of questions that are in the chat, feel free. But if you have to go, we've been going 36 minutes over the time we booked, so I totally understand.
yeah. Well, if you want to point out maybe a question or two specifically,
Yes.
I'd be happy to answer.
Yeah, I'm not. So there are a few questions. So Eric, I'm not sure if you know about those companies. He mentioned Synopsys and Cadence, and they have been working on automated semi circuit design. Do you know about their work, and do you have thoughts about that? Is that something
Yeah.
similar? Yeah.
Well, here's what I would say, and it's not my specialty, but the way that my understanding of that. So when you make the chip, you need to design it, and then you have to actually build it. So the designing part is the part that for already many years now, to my understanding, decades even, they've already been computer aided. And I think what you're referring to with the synopsis and other there, it's computer aiding of the design of the chip. But it's like, I think of it as blueprint for building a house. Once you design it, somebody actually has to go and make it look like how they asked it to look like. And often that's the bottleneck, and that's where we come in. Lam builds the machines that makes the chip, so there's usually in a given chip 500 to 1,000 individual steps, and some of those steps are the bottlenecks to actually building like that high aspect ratio structure that Rick showed, that whole. So that part, the building of it, the processes that build the chip, that's the part that we're talking about that just hasn't, it's been manual for the last 40, 50 years. And we believe this paper is representing the beginning, the initial stages of being computer aided. Does that help? So one is the
Yeah.
design and one is the building of it.
Yeah, I think that makes a lot of sense. And kind of most of us question kind of build a little bit on that, and I will reframe them a little bit based on your answer. So do you think that this human machine collaboration will be limited to the current computer? Do you think later on with quantum computer developments that will also be possible or something we will do, or do you think by then the
Well,
human is done?
as much as I can guess, I would say that what we did, I think it could be used to find a recipe for a cake in the kitchen, because Rick didn't want to generalize, and I won't be able to completely generalize either, but there did seem something, we've seen it in chess, and we were seeing it here, where the human gets things started, and then the computer algorithms can jump in. And so there's no reason for me to think that it wouldn't help in some other area, or however it moves in the next few decades, not knowing exactly how it'll be done.
BTR, did you want to follow up on that?
Yeah, thanks, Katrina. Hi, Karen. Thank you for this, wonderful talk. I was wondering, so is the optimization is where the steps are reduced to, say, build a chip, or the processes involved, and are there any rate limiting steps that you cannot bypass, like just by statistical learning techniques.
You mean, are some steps so hard that the computer or the human just can't dial it in and find an appropriate process?
Yeah, so for example, like some steps that are like causally related, or like, that you have to complete this process before you begin the other, and there is no way around it, even if you explore the entire space to or the algorithmic space, or in this case design space, I guess.
So
uh, do,
I think what I'm hearing is that are there places where sometimes we think it's impossible to find a process for a given step, and that's always a really good question, because we always say that in any given process we've never tested all the possibilities, but there's definitely, the customer gives us some really hard problems, some really hard steps. So we're always at the edge of something we think we can't do, actually. So we might be able to do 50-1 or 80-1 aspect ratio, and the customer will then ask us for 85-1, right? They're not going to ask us for the 120-1. And over the years, we just keep pushing the limit further and further. But on a given process with a given, I think that the really, really hard processes, those are probably not the most amenable to this human first computer last. Maybe because the human hasn't really initiated and given enough guidance to the computer, then this method may not work as well. But for the 90% of processes that we know have a solution, we just don't know how quickly to get there, it costs a lot of money to find it, then I think this method is more suited for those.
Got it. Yeah, I always felt like chip design and etching and all, like these are already automated processes now. And I had few friends who were in chip design, and they do use all these tools to um, help them design. So this puts a little more, I guess, spin on the workflow, right? It puts more.
Yeah. And over the years, again, I started 20 years ago as a process engineer, and I also feel like, haven't we done enough of these processes that we just already should know what the recipe is? But it's as if every single process on a different stack, on a different tool, with different specs, every single one is like, almost feels like we're starting over again and has to be retuned. And even to the extent that you've already found a process that meets the spec, you might even go to a different tool and it's been upgraded and it no longer meets the spec, and you need to go and you need to re-optimize it and redial it in. Even on the same tool tomorrow, it may not meet the spec and you need to redial it in. So it does still, I think the people who haven't been in it, that's why I thought initially the data scientists thought, oh, this is an easy problem, just tell me all the numbers, I'll just plug it all in. How come you guys can't figure it out? But really, every process, it's almost like we have to do it over and over again. Although they're not all super hard. Some of them you can dial in 10 tries, and some of them you need 1,000 tries.
Yeah, thanks for that. And the sorry,
Yeah.
get me
Oh,
one
go
more.
ahead.
So is there any exponential aspect to certain specs that you get, that the it gets exponentially harder to go about it based on like the current resources you have, say compute resources and stuff? Like, does it get is it polynomial, or is it like?
Yeah, I'm trying to think. I mean, I would say it feels exponential, but I think it's kind of regulated, because if the customer thinks you cannot reach it, then they'll relax the targets a
I
little
see.
bit and they'll adjust their design. So if their design comes out and it says we need to etch something that's 500 to 1, they don't even bother asking
Right,
us.
right.
Yeah, so kind of self-regulates in that
Yeah,
sense.
thank you.
Yeah.
Yeah, thank you so much for answering that. And if you have like another minute, Mustafa asked, the robotics that for manufacturing the semiconductors, what kind of development in the robotics would enhance improving that workflow? And do you also, run models for this basically?
Yeah, so this study didn't address the robotics or the AI of the actual machine that runs the reactor or the moving the wafers back and forth. That's another aspect in the industry that that we do use AI and we do use robots for. This paper was this paper was more about the process, and that part we hadn't really seen a lot of attention on. So that's kind of the area in the semiconductor industry that hadn't really been utilizing the power of AI.
Yeah, thank you. But yeah, so probably it's an interesting future project maybe. So that's yeah. And what are you excited about to work next on, or what are you working on? I don't know if you can disclose anything, but like just generally speaking, what can we kind of expect a peek in the future?
That's a good question. I think I'll just answer the way before you said what are the exciting applications. Watching every time a process engineer comes and says, "Hey, we did this process and we used this method and it worked," and they show that, it's super exciting. So I see that transition taking place. I feel like we're when we look at self-driving cars, I live near Mountain View and I see all these self-driving cars going around. There's always a human in the car seat still, and I look at them and I think, oh, you guys are the one of the first. And so I look at these process engineers coming to us using this method, and I'm thinking the same thing. You guys are just at the beginning. You're one of the first who can say that you've been driving this process with a computer next to you, and that part's really exciting to watch.
By the way, Karen, I'm close by and I see those cars been driving around for a couple of years now
For a
with
lot less
humans
so
in it.
lately.
With the humans in it.
Yeah, there's always human there.
I wonder when they're going to be driving by themselves.
Right.
Well, yeah, it's always wonderful to see basically the real world taking up the work, that you've been working for many, many years and then turning it into reality. I think that's always very exciting. So, yeah, thank you for sharing this work, for staying on longer and answering our questions. This was a really exciting discussion, and yeah, I'm really looking forward to the future. So thank you so much, and enjoy the rest of your evening. Thank you.
Sure. Thank you. Glad to be here.
Yeah, and thank you everyone. Oh, Joyce, did you want to?
I just wanted to say thank you to Karen and thank you to Katerina and everyone.
Yeah, wonderful. And thanks everyone for being here. It was really interesting, um, the discussion. And we actually have in 10 minutes our science news update room. So if you want to come and hang out and listen to what's going on in science this week, and then we can figure out if we invite what guest speakers we'll invite in June. So yeah, if you want to participate, feel free to switch to the next room in a few minutes. So Thank you, everyone. Karen, I hope we'll hear you again one day. It was wonderful meeting you. And yeah, we wish you all the best for the future.
Sounds good. And this sounds fun. I'm gonna tell my my uncle and my daughter about these talks that you have.
Oh, wonderful. Yeah, we love having more people participating. You know, that's the cool thing about, I had like a list of questions that I sent Rick, and I think it would have been very boring just going through my questions. So it's really so much more fun if more people come from very different backgrounds and ask things, because it will turn the discussion into so, yeah, much richer. So yeah, feel free, and thank you for suggesting that. Thanks.
Okay, great. Bye, everybody.
I'll close the room in 3, 2, 1. Bye, everyone. Thank you.